At precisely 10:18 a.m. on March 28, 2025, a three-man HIMARS crew received the two words they'd been anticipating: batteries release. Within moments, the most advanced rocket artillery system ever fielded would unleash a devastating precision strike on one of Europe's key energy hubs, transforming an otherwise quiet morning into a textbook military operation that will be studied for decades to come. The crew had only been on site for just under 4 minutes. Their M142 HIMARS launcher, mounted on a nimble 6x6 chassis weighing roughly 16 tons, remained motionless as its hydraulic stabilizers locked it into a firing stance. The engine stayed running, because once the rockets launched, they'd have less than 5 minutes to vacate the area before enemy counter-battery fire could arrive. Inside the vehicle's cabin, the section chief was finalizing data on the Universal Fire Control System, UFCS. This digital brain combines GPS coordinates, atmospheric conditions, ballistic modeling, and encrypted targeting data relayed through secure satellite communications. By this point, the system had already locked in ideal firing angles, flight paths, and detonation timing for the twin rockets loaded in the six-pack launch pod. Those 2 GMLRS rounds weren't ordinary munitions. Each one packed a 200-pound high-explosive warhead, capable of smashing through fortified structures, and each was equipped with a dual guidance suite: GPS and inertial navigation for last-second corrections. Thanks to these overlapping systems, even at their maximum range, each rocket had a circular error probable, CEP, of less than 15 meters. And despite that cutting-edge tech, the system remained astonishingly easy to operate. Once the fire solution was ready, launching both missiles took a single button press. The onboard computer handled everything: trajectory plotting, synchronized launch timing, and terminal guidance for coordinated impact. Each rocket would follow a unique flight arc to confuse defense systems, yet still arrive at the target within the same instant. At exactly 10:18, the gunner hit the button. The first missile erupted from its launch tube with 10,000 pounds of thrust, a roaring column of flame and exhaust, blasting through the deflector plate as the rocket leapt skyward, hitting speeds of 2,300 MPs in seconds. 15 seconds later, the second round launched. A deliberate delay designed to mislead radar operators. Though taking different trajectories, both missiles were aimed directly at the Sudzha gas facility and would impact within seconds of each other. By the time the rockets vanished into the morning sky, the crew was already executing their exit plan. The driver shifted into gear, and the stabilizers quickly folded back into the vehicle. In under 90 seconds, they were already on the move toward their next fire mission, leaving behind nothing but scorched tire marks and the sharp scent of burned propellant. Back at Sudzha, no one had a clue what was headed their way. Meanwhile, high above the Russian countryside, 2 GMLRS rounds were mid-flight, conducting one of the most refined terminal guidance maneuvers in modern warfare. At over 2,300 mph, each missile made constant micro-adjustments, hundreds every second, ensuring unmatched accuracy on a target they wouldn't even see until moments before impact. The lead rocket peaked at 45,000 feet before beginning its final dive toward the facility. At that altitude, its GPS unit received flawless satellite signals, allowing for real-time positional corrections right up to the final seconds. The result? A surgical strike that could hit within meters of its mark. GPS alone couldn't deliver the pinpoint accuracy this mission demanded. That's where the inertial navigation system took over. Embedded in the nose of each missile, ultra-sensitive accelerometers and gyroscopes inside the inertial measurement unit, IMU, tracked even the slightest shifts in motion and orientation. This onboard navigation system acted as a failsafe, immune to electronic jamming or signal spoofing attempts by enemy forces. By combining GPS with inertial guidance, the missiles could maintain lock on their targets even if Russian electronic warfare assets tried to disrupt satellite signals. Their flight paths weren't arbitrary either. They were meticulously crafted to avoid radar detection. Instead of heading straight in, both rockets took terrain-hugging trajectories, skimming low to the ground to stay beneath radar coverage for as much of the journey as possible. The first rocket closed in from the northwest, while the second approached from the northeast, angles chosen intentionally to confuse and overwhelm localized air defenses. With descent speeds reaching 60,000 feet per minute, the final stretch from sky to target lasted mere seconds. In theory, Russian air defense units could attempt to intercept, but between the rocket's incredible velocity, minimized radar profile, and adaptive terminal guidance, the odds of a successful shoot-down were slim. As they closed in on the final 30 seconds of flight, their proximity fuses activated. Small radar systems measuring altitude in real time, recalculating the optimal detonation point many times every second. At exactly 10:20 a.m. both rockets entered their final homing phase. The onboard processors began adjusting their trajectory 50 times per second, guiding each warhead with surgical precision toward its preset coordinates. These targets weren't chosen randomly. Someone had detailed, actionable intel on exactly which facility components needed to be neutralized to take the Sudzha gas plant offline permanently. The rocket's sensors acquired the facility just 15 seconds before impact. Inside each missile, a 200-pound warhead was seconds away from proving why the HIMARS system has fundamentally changed the face of modern combat. These weren't just standard explosives. Each warhead was a specially engineered, shaped charge, designed to obliterate reinforced structures with ruthless efficiency. The core explosive, PBX-1109, detonates at a velocity of 26,000 feet per second. But its raw power isn't what makes it lethal. It's the way that energy is channeled. Each warhead features a carefully crafted copper liner, shaped like an inverted cone. Upon detonation, this liner collapses into a hypersonic jet of molten copper, traveling at over 30,000 feet per second. This jet is capable of piercing through 3 feet of concrete or 2 feet of armored steel. But the GMLRS warhead doesn't stop at breaching armor. Wrapped around the shaped charge is a fragmentation sleeve, packed with over 180,000 pre-formed steel fragments. After the initial penetration, these fragments detonate in a controlled blast pattern, shredding everything within a 15-meter kill radius. In one coordinated strike, each rocket functions not just as a penetrator, but as a weapon of total interior destruction. Each warhead includes multiple fuse configurations, customizable during mission planning to match the nature of the target. In the case of a complex like Sudzha, the warheads were most likely equipped with a delayed fuse, designed to breach the outer walls before detonating deep inside for maximum structural and operational destruction. These fuses can be set to delay detonation by up to half a second after impact, giving the warhead just enough time to burrow through barriers before going off. But the GMLRS warhead has more tricks up its sleeve. In addition to high explosives, it carries incendiary components, specifically magnesium-based elements that combust at 3,100 DGC. These practically ensure ignition of any combustible material they encounter upon detonation. In a facility dealing with natural gas, like this one, over 40 million liters of gas are moving through pipelines at any given moment. If everything worked as intended, the design of this weapon would be validated in under half a minute, assuming Russia's defenses couldn't shoot the rockets down in time. At precisely 10:19 IEM, Russian radar systems finally picked up signs of the incoming threat. The 76th Air Defense Regiment, tasked with shielding high-value assets in the Kursk area, had less than 45 seconds to detect, lock onto, and attempt to neutralize two GMLRS missiles streaking in at speeds exceeding 2,300 myths. What came next illustrated why even advanced defense networks often fail against next-generation guided munitions. Initial contact was made by an S-400 long-range radar installation located 15 kilometers southeast of Sudzha. This radar, capable of identifying targets over 400 kilometers away, detected two high-speed, small-profile objects incoming from Ukrainian-controlled zones. But finding a GMLRS isn't the same as consistently tracking it. The design of the missile minimizes its radar cross-section, presenting a signature no bigger than a large bird. Its blistering speed and low-altitude approach made it a nightmare to keep in radar lock. The S-400 system's processors kept acquiring and losing the target as the rockets danced through their terminal guidance corrections. 30 seconds before impact, the Russian systems launched their counterstrike. 248 N-6 interceptor missiles blasted into the sky, each equipped with a 143-pound proximity fragmentation warhead and guided by advanced targeting algorithms to engage multiple threats simultaneously. These interceptors can reach speeds up to Mach 6 and are built to destroy fast-moving targets mid-air. But they launched too late. The S-400's engagement cycle requires around 60 seconds to generate an accurate intercept solution against such fast projectiles. With only 45 seconds from detection to impact, the interceptors were still building speed and chasing coordinates as the rockets began their terminal phase evasive maneuvers. The final approach of the GMLRS made a hit nearly impossible. Each missile made split-second micro-adjustments to its course, throwing off prediction algorithms and frustrating the Russian fire control systems. The interceptors came within 200 meters, a near miss in human terms, but meaningless at those velocities. What made things even worse for Russian defenders was the two-pronged attack. The missiles closed in from different directions at the same time, forcing the S-400 to divide its focus. This classic pincer saturation tactic floods defense systems with simultaneous threats, reducing their effectiveness. With just 20 seconds left on the clock, the battery commander issued a last-ditch command to use close-in weapons. Two Pantsir S-1 short-range defense systems sprang to life, unleashing their 30 cannons in a desperate barrage. These systems can fire up to 5,000 rounds a minute and are optimized for threats like rockets and cruise missiles, but at 2,300 pints, the missiles were moving at more than 1,000 meters per second, far too fast for even that wall of fire to stop. The gun-based defense units had only a split second to lock onto, track, and attempt to intercept targets that were already commencing their final descent toward the Sudzha gas complex. Streams of cannon fire lit up the air, trailing just behind the rockets as they sped past, unimpeded. Russia's last line of defense had completely collapsed. By 10:20 IMM local time, the first HIMARS missile slammed into the Sensa facility's main processing core. Moving at over 2,000 media, its 200-pound warhead tore through the facility's reinforced concrete barrier like it was thin plastic. The shaped charge directed a focused blast into a concentrated jet, slicing deep into the highly pressurized infrastructure before detonating. The explosion erupted within the gas compression system, where pressure levels were maintained at 75 times the normal atmospheric value. A shockwave traveling at 26,000 feet per second ripped through the chamber, instantly breaching high-pressure pipelines and obliterating critical containment safeguards. In a fraction of a second, vast volumes of compressed natural gas started spewing into the facility's interior at uncontrollable rates. But the true devastation had only just begun. Exactly 15 seconds later, the second HIMARS rocket struck the facility's central command center. This missile had been configured with a delay fuse, allowing it to punch through structural barriers before erupting within the SCADA control room. The resulting explosion vaporized the electronic systems that could have activated emergency shutdown protocols. The interval between these two strikes was intentional and calculated.